AP exams, what classes do you actually attend? Because
Not a lot, I think,
We don't have to attend any classes on the day
of an AP test, as far as I know. But you better get that squared. Every year, somebody decides different, so I'm not in charge of that, unfortunately.
For your classes, do you have to show up for class when you have an exam?
No. I'll just tell you that right now. If you got any other AP exam, you're out for the day. You're out for the day.
Are the AP
Okay.
exams taken here at your
yeah,
I have no idea. Okay,
Even though
so
everybody else is school?
I'll tell you and folks at home, I just sent to you in the Google Classroom stream the given information, and you'll have a clean copy of that both for the Clausura Monday and for the actual AP test, as well as a clean periodic table. So you'll have that to use again for the whole Clausura. Okay, so good. You can kind of check that out ahead of time. When the bell rang, we just were in the middle of dinking around with this equation. And I want to review what we did, especially for folks at home. I gave you before break that we got a magnesium stick in magnesium nitrate solution, a copper stick in copper nitrate solution, and this thing called a salt bridge in between. We'll see what it does in a little bit. For now, though, let's review our equations. We found two different equations, and we decided to flip this one. Why? Who remembers why? Lena?
Because the MG was on the wrong side. We needed it on the left and it was on the right.
Good. Exactly. So we need something like this. When you have a bunch of equations, you need something higher on the left, something lower on the right. And once you find the two equations, pick the item that's on this side, the reactant side, and here on the product side. And then you're going to take this and flip it. Now, let's tell you why you're flipping it. These are all reductions, including this one. And I've got to flip this because I've got to make this one be a reaction. Oxidation. You see now why you got to flip one? If one is like, what's reduction? Gaining electrons, then the other's got to lose electrons. So flip, so it's oxidation. Right? So you want one that's reduction and one that's oxidation. And you're going to flip it with that pattern because when you use that pattern, you're going to get a positive voltage. Let's see what we get. I'm sorry I wrote this here because it looks like it's negative. Okay, so my two voltages for the top equation was 0.34. For the bottom, it was negative 2.37, but we flipped it around, so we made it positive. Good. Let's add it up, and I get what? 2.71. And that is a pretty high voltage, to be honest. So it means a number of things. It means it's very exothermic, and it's got a K that's much bigger than 1. And its delta G value would be negative. Delta G is gives free energy. When it's negative, that also spontaneously is what's happening. Did I screw something up, Ray?
No, I don't think so. I just don't completely understand that when we flip it to make an oxidation, wouldn't like we flip that circle to the other side as well, and then wouldn't it be less? Or am I misunderstanding something?
The simple answer to your question is if I flip the equation, then I've got to have it as then 2.37. Now, the more complex answer is at the back of the book. Oh, hello, data. There it is. Page 569. Right? Page 569. These are all of these suckers are written as reductions. And it kind of goes like this. They do the positive ones at the top, and they get more and more negative as you go down. What that means is the ones at the top are all spontaneous. The ones at the bottom are not going to happen at all, as written. So you want one thing to make a battery, to make a electricity flow through the wire. We want one thing that's going to undergo reduction and one thing that's going to undergo oxidation. And you got to have it, so you want something higher energy. Well, that's going to be something with a positive voltage. That's, God damn this mask. Christ. So sick of this crap. Ugh, you are too, I know. Okay, so I got to have something with a positive voltage, so I'm going to have something up here. That's why I say the top side, the reactant side needs to be above the other side. And then I need something that's going to oxidize. It's going to be lower down on the right side. And then I got to flip that thing around to make it into an oxidation instead of the way it's written in the book, which is as a reduction. So did that help a little bit?
I think, yeah.
Okay,
that's clear.
all right.
Thank you.
We're going to have you try one too real soon. No,
What does that voltage represent? Like in terms of this diagram,
good.
what is it referring to?
Good question. What does that voltage represent? It represents the force that electrons feel to make a move. Let's go to our equation for a second, okay? Oh, we didn't finish it. God, bad teacher. Okay, we agreed the electrons cancel. And so on the product side, who's sort of seeing what I'm doing? I'm going to get what on the product side? When?
You're gonna get magnesium 2 plus and copper.
Thank you. What that means is we got to come over here and think about it logically. Who is losing the electrons? Look at the equation, see if you can figure it out. Who's coughing up the electrons? It would be
Let's see.
Cu is not.
So Mg.
Okay, let's figure out why. Cu is a positive ion, and it's becoming Cu on the other side. So to become the positive ion,
Oh yeah, I mixed it up. I mixed up the yes.
exactly. So now say it in words. Now, to become zero charge, it's got to take the 2 plus and add
It's 2 electrons.
2 electrons, exactly. Okay, so that's going to be taking the electrons. So therefore, who's given the electrons? Shopa. Magnesium. So watch this. Oh, this side is magnesium. Just because I wrote my picture this way. So the electrons are going from here to there. You want to be able to put an arrow on your wire by using that logic. So make sure you know electrons are coming from, going to. Now follow the electrons. Ready? Now let's take what Noah B said. We're making more copper, right? Copper solid. Look at what that means. We're making copper ions grab onto this electrode and make it bigger. So what that means is this sucker's going to gain mass. The Cu stick, or electrode as it's called, will gain mass. I make more copper solid. What happens to the magnesium stick on the other side at the same time, Quinn?
The magnesium will dissolve.
Exactly. So I'm making more ions,
Right?
and this is going to essentially go like this. Pieces are going to get eaten out of it, holes or whatever. So this is going to lose mass. This electrode loses mass. And my poor people at home can't see that. So this electrode loses mass, this one gains mass. How do you know that? Look at our reaction. Let it guide you. Oh, solid is becoming ions, aqueous. Therefore, I have less and less solid. Here, the ions are becoming solid, so I have more and more solid copper forming. It'll be a measurable amount. At the end of the chapter, we'll figure out how to determine how many grams you're making. Oh,
Do we always have to write the aqueous solid?
No.
Doesn't matter.
no, I'm just doing it here to make you think.
Okay. Do we ever have to write them on the?
If they ask for it, sure.
Okay, but only if they explicitly ask.
Yeah, I mean, they'll ask for it if they want you, or if you needed to talk about gases or something in your discussion. So, but normally, no, I don't have to do it, but here I want to because it's so important for figuring out who gains and loses mass. Okay, now, let's add some words to this thing. Words? What do you mean, Mr. Weiss? I mean, okay, what's happening? The magnesium is undergoing which one? Oxidation or reduction? Look at our reaction. Let's go into Mg2 plus from Mg. So, Lena? Oxidation. Good. So this is oxidation here. And the other obviously must be reduction. Let's verify that. Cu2 plus reduces to Cu. Yeah, the charge goes down to 0. That's how I always do it because I'm too lazy to think about it in another way. So I got oxidation, I got reduction. There's two words, anode, cathode. One of these electrodes is called the anode, the other is the cathode. Here's how you're going to remember it. Anode and oxidation both start with a vowel.
That's a bit of.
Oh, no, a vowel. That's the anode. So oxidation always happens at an anode. Cathode and reduction both start with a
Consonant.
consonant. Thank you. Okay, so this is the cathode over here. What are those? What are they? They're just pieces of metal, gang. The anode and cathode are both pieces of metal. They could be something else. They could be carbon. They could be platinum. I don't care. But they're where electrons are either being gained or lost. Here they're being lost. Whoop, here they're being gained. And then it grabs onto copper ions and grabs onto here and makes more mass. Real.
Could one also remember it when mixing anion and cation? Yeah, because like it's anode and cathode, and I immediately thought of anion and cation.
Good. So an anode attracts an anion. Ooh, let's write that. Anode attracts anions.
That's why they're called anions, right?
Yeah. In fact, we can then put a charge. So what charge would this sucker have if it's attracting
That
anions?
would be positive.
And the other-
cathode is negative.
You got it. Isn't that fun? It's all logic if you just think about it. But chase it down slowly and think about it with me, okay? It's all logical. So anodes or anode attract ions, and we got oxidation. Both begin with a vowel. And then we got cathodes attract cations. And so we got reduction happening. And if it attracts cations, then it must be negative itself. Just think about it. Opposites attract. Or did I screw up? Quinn?
You didn't screw up. I'm thinking there's an excellent opportunity for a joke about onions somewhere in there.
About onions?
They're either on ions.
About ions. I'm sure there is. Can I think of one off the top of my head?
But I believe so.
Cations are positive because everybody like cats, feels positive about cats.
Cats
okay.
generate positive feelings and
Onion
generate
make
negative
cry.
feelings.
And onions negative feelings, so it's attracted to the positive pole. Okay. Make up an acronym or whatever of your own choosing. No B.
So what's the point of all this?
Boy, that's a great that's a great question.
I mean, like chemically, not in my I mean, also like.
No. Your question's good on a number of levels, Noah. But the first way it's good is the point of all this is understanding batteries. In other words, really concretely, stuff that runs your handy, stuff that runs your flashlight, runs whatever, is using some sort of system like this with a cathode, with an anode,
Is that the
and somehow
opposite?
electricity is flowing. Now, it's not liquid, it's solid or a gel, but it's the same idea of flowing electrons. And it's always going from a higher potential energy to a lower, just like in our book, high on this side, lower on this side. The same rule works for all the batteries you use in your lives.
Isn't it just potential and not potential energy, or is it both, or like higher?
Yeah, you can call it electrical potential, and it's talking about the potential energy of the electrons, if you want to look at it that way.
So, yeah.
Electrical potential, then same thing, right?
How would we encounter this on the AP then? Would we like have that? Or how would a question about this be phrased?
It would be, let's make it an FRQ. You ready? Okay, FRQ. In the diagram up above, electrons are going which direction, and justify your answer, part A. In the diagram up above, the
Or you-
electrode that's losing mass is which one? Explain your answer. Balance and write down the redox reaction for this diagram and give the voltage, part C. You know what I'm saying? It would be broken up, but a lot of the things you and I are doing could be separate parts of an FRQ.
I don't know. I was thinking about something. Not a joke, it was an actual scientific thing.
Well, that's okay. If it comes back, that's fine. No.
A few things. First of all, is that at the top, is that like a voltmeter?
That's a voltmeter. So this would register, ding, ding, ding,
Voltmeters are
Two-
in parallel,
2.71.
voltmeters are in parallel to the circuit, not in the.
Then make it a parallel circuit running through it. I don't care. Okay.
And then the salt bridge, it's like, what's that? This, I think you showed it to us in the first period.
Yeah.
Is that full of salt? And
So what the heck
bottom
is this
open?
for? So it's full of salt. So what, Mr. Weiss? Why do I need this damn thing? Okay, let's have a look and see. Okay, well, what happens is I'm making copper, right? So I'm losing copper ions. Oh. But I can't do that in a solution. I can't lose positives. I've got to replace it with somebody.
Or
So guess who's going to come down here and replace it? Some NH4 plus. It comes through that semi-permeable end right here and replaces it to keep the charge neutral. I can't suddenly have less positives. You know what I mean? So now this will come, and essentially I'll have less copper 2 pluses, but I'll have the same amount of positive ions on that side. I have to keep it electrically neutral. And on the other side, hold your questions for just a sec, the opposite happens. Here, I'm getting more and more Mg2 pluses. Whoa, I'm just creating them all over. Yeah, you know what? You can't do that unless I also make what come down here to match those. The nitrates. So here I got at NO3 minuses, join those. How many? Well, the same amount of Mg3 pluses that I have made.
what's the number?
I got to have, or twice the number, thank you. So, well, the same amount of charge in Mg2 pluses. You got it. So to balance the charge. Now your questions, yeah.
Okay, so thinking of it as a battery, like it would be empty when all the Cu plus would be gone?
Yes.
Okay.
Or when all the Mg is eaten away and is gone.
You would recharge it by, would you be able to recharge that?
That's a hard battery to recharge. Somehow you'd have to put all of the Mgs back onto here by making them take electrons again. And you'd have to get rid of a bunch of Cus here by making them cough up their electrons and become an ion again. This type of battery, probably practically speaking, would not be rechargeable. But the ones you use for your handies, of course, are, right? We know they are because you can charge them over and over and over.
How would those work? Like they haven't.
They're more complex, but the basics, cation, anion, anode, cathode, the basics are identical to this,
You know, like what
but the
material-
chemicals are different.
What materials and how would they design that?
Oh, there's lithium and stuff in there. They might even have it in your book. You can look and see if that battery's listed as one that is in a diagram in the book.
what is the original solution that's all in, like,
Ammonium nitrate in this case, but it could be
No, but
any
like
salt.
the liquid, like what is it in?
What was it originally?
Yeah,
Magnesium nitrate solution here, and over here, copper nitrate solution. Copper
The
nitrate.
color for copper.
And so the nitrate means it's really soluble, so it makes a good solution to have in there because they're not sticking together. It's all dissolved totally. Good questions from you. Anything else? Okay, your turn to do one. You ready? So what I'm going to give you is instructions, and I want you to do this entire board, and you can work with someone else if you want to do it. Entire board with a diagram and the voltage and the arrows and everything for a couple of metals. And if we have time, we'll put it up here. If we don't, we'll put it up next time. Like on Thursday. And folks at home can try this as well. So do all this, top board. With silver and silver nitrate. Oh, actually, I could do it and show you something else too. You get a twofer here. Ready? Silver nitrate. All right, now check your stuff. Teacher, are you doing it right? I think so. I might be doing it wrong. Let's see. And let's just have magnesium again. Mg2+. Except I think it's got to be the other way around. I may have to fix that, and the solutions, silver nitrate and magnesium nitrate. One molar, by the way, because those are the standard solutions, 1 molar in terms of concentration. With Ag and Mg metals. But I'm not going to tell you which one is which. Okay, that's it. Go ahead and try and make a picture and then try and figure out which way it's flowing. Look up the reactions in the back of the book. If you don't have a book, share with each other, but you'll need that page. So folks at home can try and do that as well. And I've got to see if I wrote it up correctly.
Do you have the solutions that we could make our own batteries?
I don't have a lot of silver around, unfortunately.
And
Gold either.
can we try it with copper?
Copper, yeah.
Can we do it?
Yeah, we probably can, but not this second. I got to figure something out first. But yeah, I sometimes do that with classes, Quinn.
Let's do it.
Okay, and we'll do it probably Thursday.
Okay, hold on. Thank you.
Okay, so silver, and what else did I give you? Magnesium. I did it right. Hallelujah. Small wonders. Okay, this is called cell notation. So I just gave it to you. It's the anode and then double lines the cathode. And if you think about it, I gave you the guts of the reactions too. So that actually can save you time.
It's in the salt bridge.
I think it's the same thing.
This is it.
Others say that's a deficit. I think so.
So it's just NH4. I mean, it would be the actual salt rather than the two ions, right? It would dissolve into the two ions.
Okay, so. Is this? Well, it's NG, NG and AG. Yeah, I think so. So the AG, okay, if it's going to AG plus, the AG, then it's coughing up an electron. So I don't think it's gaining an electron. You know what I'm saying? I think your arrow's going the wrong way. Because I don't think this is quite right. Like the AG, that or I wrote it wrong. Wait a minute, I might have wrote it wrong. Nope, you're right. And I'm wrong. I hate it when I'm wrong. It happens so often. Okay, so here we go. I wrote it wrong. The cell notation has to be AG plus, going to AG, and then MG, going to MG2 plus. So you're right the way you drew it. No.
Okay.
But my notation's wrong. So that's the right way to write the notation. And that's the anode and the cathode. And you're missing some stuff. I hope you realize that. Okay?
Yeah, I need alligator clips, I need the salt bridge.
get that far, compare notes with each other, see if your pictures look similar. And your redox reaction should be identical. And your voltage should be the same as each other's as well.
Is anybody done?
I don't think
Uh, you said yours, okay.
Yeah, Adrian's next. Oh,
When you drew the arrows, right?
but Adrian,
Well, he,
sorry, Adrian Games.
look, he basically just writes it, look. He says it's anode line and then the cathode. That's how I did, like, he just writes it. Oh, look, I'm on screen.
If I did it like the way we did it before,
Yeah.
then it's like, I did this, and then AC would be gaining an electron. Which would mean
Oh, yeah, okay, I understand what you're saying.
it's the cathode. I don't get what you did there, that's why I don't understand.
Poison free.
Right. I just wrote anode and cathode based off of that. I think you're right. Right, yeah, because it gains mass
Yeah.
when it's a cathode. Because it attracts. Okay, so yeah, so you're right, this must be. What was your voltage?
3.1.
Wait, how do you know which one you have to
Although I
flip?
have the same numbers.
So do you know which one you have to flip?
It's the one that has a smaller voltage. You have to put that one.
Okay, how you doing?
You have to take the right side.
Like smaller in terms, like on a number line smaller? Like is
Yeah,
negative 2.37?
Let's start to put it up there. So you want to put up a picture and maybe Noah, a picture and maybe the redox, one of you the picture, one of you the redox.
Oh,
And our consultant is doing redox.
You wanna do the picture?
Sure.
have fun.
Voltages.
I want red.
And labeling and stuff. So please be the consultants for these.
I know, right? I'm just really an amazing person.
We're great
consultants.
Your drawing's wonky.
Hmm?
Your drawing's so wonky.
She's complaining about everybody's drawing. She said my drawing wasn't that great.
We're chemists, not artists.
I've tried to use that line, but not always effective.
I might become a teacher just to like write on a blackboard.
I mean, by the time you're a teacher, there probably won't be many.
What's going to be the problem?
I'm gonna be old fashioned.
Where are we doing the voltages?
Oh, are we just supposed to do them? Okay.
We're
supposed to
the
sound
salt
good.
on yours, but we can do.
Oh, is mine right?
Yeah, it is, but
I'm so smart.
0.8
Wait, was I supposed to write the voltages?
Yeah. 0.8
You can still use it,
plus
Yeah.
2.37
but there's a problem. What will happen to the voltage?
equals
This is really good.
3.17 volts.
In math wrong.
No? What did you do? Did you
Three
double?
point two one. 7 plus 0 is 7.
Oh.
8 plus 3 is 11. You're right.
Yeah.
I carried a 1 for no reason.
That's it,
Yeah,
right?
it's annotation.
You do volts on each.
Version of how chemists write stuff.
What else am I
They
missing?
put the anode first, and it's like AG plus is going to AG, and the cathode second, MG is going
Am
to
I not
MG
missing the
plus.
like?
You are missing. Do you
Unless you
want
get a
Yes.
voltage.
I didn't get that far.
to? You want to do it in the
So
cool
it might
colors
be a
then?
nice readout.
Sure.
So
I
let's
thought
see.
Adrian would gain it.
Yeah, it does. So what do I got? I got was the anode.
So you would flip it.
So it doesn't matter. It's one
Yeah.
of these.
So I'm again wrong. Oh, it's so hard to find good teachers, but it's easy to find good students that catch all my mistakes.
Okay.
Okay, so shall we try it? MG2 plus, and
And then nitrate.
Shilpa. Does that look better?
Why do we, how do we know that MG2 plus is,
Because it has to be able
Does that look better, Shilpa?
Yeah,
Thank you.
Here we have
Right.
AG.
I know what's wrong when I put it up. I didn't do it double wrong. There it was.
Do we want to round it by choice?
Is it like, yeah, I know, but it, I know, but we're just
Like,
like.
do you want to label them as capital?
Site. Oh, wait, don't we?
Oh, really?
But not, like, we're taking them, you know, the input.
Do we want to do
Or are you saying?
excellent, proper alligator.
Yeah. Wait, how many years is
It's such a fail.
It's just,
Yeah, that's what
it's lonely.
And folks in the studio audience,
Sure.
you've got a battery we're gonna hook up next time. Got some copper solution. Zinc. Is it? Yeah, zinc solution. I've got a piece of copper, piece of zinc, and I've got a voltmeter. So we'll hook that up on Thursday. We won't do it now because we're, just.
How do you know that electrons flow this way?
I'll save it on my electric card for us to do.
Guess what?
Well, here we have it turned
Oh, that's,
into this
I thought that was,
research.
We have,
But according to this,
yeah, that's true.
that's the case here as well.
no, look at the one up there.
Yeah.
Actually,
Look, I had to do this today.
it's future.
And one of them is
17.
turning
Each one was
into
like full of.
this salt, more of the solid, and one is turning into.
I heard that one of those, like,
Wait, Mr.
What was
Wise,
that called?
can you explain like why the electrons are flowing one way or?
Yeah. So the one that's higher is the one that's gonna be undergoing reduction. So it's this one. So I'm gonna make more silver. So which side is your silver? I'm gonna make more of this. And it needs electrons to attract these little silver ions to here. So the electrons are coming down here, and I'll get more and more mass of the cathode as time goes on. And
So
so then I've
where
gotta
the-
break up this one.
And where are the AG plus ions coming from?
From the
this?
solution, it's a solution of silver nitrate.
And that's already existing before you put
That's this
in.
blue stuff. That's all that in there.
Okay,
And then this is a chunk of solid silver, so that's different.
okay.
You have to have both the ions and the chunk of metal each
Yeah.
time.
Nice.
You're welcome. Okay, my people, well done. Let's have a look at everything. Let's see if I can find any of your mistakes, except that I don't really see any. Folks who did the reaction here, we have one, and that's 0.8 volts. The second one, again, you had to do what with its voltage value? Flip it, good. The top one, you had to multiply by 2 to make the electrons cancel out. Did you have to do that to the voltage? Correctamundo. No is the right answer. So we just add those two together. That's your voltage, and that's a very high voltage indeed.
Why do you not have to multiply it?
Good question. Here's the electrons. We say they're dropping in energy in the similar way that things drop because of their height. So, okay, if I double it, I just double the amount of them falling, but I don't change the height. If I change the height, that would be a bigger voltage. So the doubling them means I've got twice as many electrons, if you like it, falling over this waterfall. But if I multiplied by the voltage by 2, that wouldn't make any sense because it means, oh, you're changing the height of the waterfall. No, it's still silver. It's still magnesium. The reduction potentials will remain the same if the metals remain the same.
So it would be the magnitude of the current that's changing.
Yeah, it's the magnitude, not of the current, but of the force that the electrons are being pushed with. So it's like, if I have this much force that I'm pushing electrons with, even if I double the amount of them, I'm still pushing them with the same force, is maybe another way to look at it. Tom?
This won't be on the right?
Sure.
Or
Yes.
Not in exactly this form, but something about batteries and oxidation reduction, of course. Yeah. Yeah, absolutely. No.
Oh, no, I remember. Do we ever change the voltage?
You can change the voltage. I'll jump ahead to Thursday. This is 0.5 molar. This one's 1 molar. If I use 0.5 molar, it's not a standard. The standard voltages are all based on 1 molar.
Oh, so then we would have to.
You wouldn't have it, but it would be less. If I use weaker solutions, I don't get the full voltage strength. I have to have 1 molar. Or if I want a higher voltage, I could do what with my solution strengths? Yeah, although you got to be careful. Let's look at our reaction that you guys did here. Oh, which one would I want to make more concentrated? The Ag2 plus or the Mg2 plus to increase the voltage? Can you guess? Which one more concentrated to increase the voltage? Nobi?
Maybe the MG2 plus because it already is a higher voltage.
Well, no. If I increase that more, Le Chatelet's principle, it's going to push it this way.
Oh, okay.
So use Le Chatelet's principle. The one I want to increase is if I add more Ag plus, Ray, what will happen?
Well, then it'll shift to the right.
You got it. And that would make the voltage slightly higher. It may be 3.2 or 3.3 or something. It's not a huge change, but you get a little change if you dink around with the concentrations and if you don't have them exactly as 1 molar. But the changes you can absolutely predict with your power of Le Chatelet's principle. Rhea?
Will we learn how to calculate that? Like if they're not 1 molar, how we calculate?
There's an
that?
equation and you don't have to know it anymore for the AP.
Yeah.
Cheryl gives it to you, but I think I tell you in the reading, you don't have to know how to do this. Yeah, so there's an equation, you betcha. Do you need to know it? No. So life is good. Okay, I'm a little exhausted. You look fairly exhausted. Let's call that good for the day. We'll make a battery next time. Finish up chapter 8. Take your questions. Hopefully have a few more people in the studio audience. Thanks for your participation, folks at home, and my studio audience. The prizes will be waiting for you at the end of the year.
The prizes can be found under your seats.
Yeah, well, that would be air, but that's always there.